everyone, this is our advanced functions review video, and we're going to be covering exponential and logarithmic applications. I'm Allison.
I'm Sam.
I'm Saad.
Today we'll be covering half-life, double-life, growth, and decay.
And we'll also be covering the pH scale, the Richter scale, and the decibel scale.
Hope you enjoy!
Hi, my name is Samantha Friedland, world-renowned earthquake specialist. I am here today in San Francisco to tell you about earthquakes and and the Richter scale. Oh no! I feel an earthquake coming! Ah! Oh man, that was a big earthquake. That was at least a 7.6 on the Richter scale.
सलाम, मैं साद सैयद हूँ और हम आप इधर टोक्यो में और मैं earthquake specialist हूँ. Earthquake's happening! Oh my god! ये कितनी बड़ी earthquake थी? It was 9.8.
So this is the formula for the Richter scale. M stands for magnitude, I stands for intensity, and IO is the original intensity. For the San Francisco earthquake, the magnitude was 7.6 on the Richter scale, and we don't know the actual intensity of it or the original intensity. So you first put it into exponential form, so you have 10 to the power of 7.6 equals the intensity of San Francisco over the intensity of the original one. Then you cross multiply the intensity of the original, so it's IO times 10 to the power of 7.6 equals the intensity of San Francisco. Then for Tokyo, you do the same thing. It was a 9.8 on the Richter scale, and it equals log of the intensity of Tokyo over the intensity of the original. You change it into exponential form, and then you cross multiply again. When you have the product of those two equations, you have the intensity of the original times 10 to the power of 9.8 to represent Tokyo, and intensity of original times 10 to the power of 7.6 for San Francisco. The two intensity of the originals cross out when they're divided by each other, and you're left with a difference between the two earthquakes of 10 to the power of 2.2. So, the earthquake in Tokyo works out to be 158.49 times more intense than the intensity than the earthquake in San Francisco.
Saad, that was at least 110 decibels, the music you were listening to. This normal conversation is only 60 decibels. Think of the comparison. So this is the generic formula for loudness and decibels. L stands for loudness, I stands for intensity, and IO stands for the original intensity. So here we are looking at the intensity of Saad's music. We sub the numbers into this equation. So 110 decibels equals 10 to the log I over IO. We're going to put that, divide the 10 out first of all, so that gives us 11 decibels equals log to the I divided by IO. And now we're going to change this into exponential form. So we have 10 to the 11 equals I divided by IO.
And then here's the loudness of the conversation. 60 decibels equals 10 log I over IO. First we divide the 60 by the 10, and we get 6 decibels equals log I over IO. Then we turn it into exponential form and get 10 to the power of 6 equals I over IO.
So now I'm going to show Saad just how much more intense and loud his music was than our general conversation. So we're going to compare the two. You saw when we were comparing the earthquakes that we can cancel the IOs when we are comparing them. So we're going to just skip that step for now. So we have 10 to the 10 to the 11, which is the loudness of the music, divided by 10 to the 6, which is the loudness of our conversation. This brings us to 10 to the 5, which works out to 100,000. That meant that Saad's music was 100,000 times more loud than our conversation.
Oh my god.
So for all growth and decay questions, there's one generic formula that we can use to help solve them. And this is AT equals AO e to the T. So in this, T stands for the amount of time that has passed. B is the base, and this is the rate at which something increases or decreases. So, for instance, in half-life questions, base is a half. In doubling questions, base is 2. AO is the original amount that you start with. And then AT is the amount that you have after this specified amount of time has passed.
These puzzle pieces represent bacteria.
just as the population of bacteria doubles after a specific amount of time, these population of the puzzle pieces also increases exponentially as time passes. We're back to our generic doubling equation. AT equals AO times base to the 10 to the divided by D. So in this equation, the original amount that we started with was 2 puzzle pieces. Our base is 2 because we're doubling. T is the 10 minutes that it took for us to reach the final amount of 64 puzzle pieces. So we don't know what our doubling time is, and that's what we're going to find out here. So first of all, we plug all of our numbers into this equation. So 64 equals 2 times 2 to 10 divided by D. Next, first of all, we're going to divide by 2 to take the 2 away from this side, so that leaves us with 32 on this side. Then we have a perfect exponential equation right here. So we're going to transform that into a log equation, which leaves us with 10 divided by D equals log base 2 to the 32. Using the change of base technique, we find out that log 32 divided by log 2 equals 5, which equals 10 divided by D. We can rearrange this to solve for D, which is 10 divided by 5. Therefore, our doubling time is 2 minutes. Since ice cream is delicious, this is going to be a half-life question. The population of ice cream decreases by half every specified amount of time. Go ahead.
Okay, so first off, you know that you're left with 2.5 and you started off with 40. And your base is a half because it's a half-life question. And that's also why, and every half minute, and half the ice cream was gone. So, and we're trying to solve for t. So first off, you plug your numbers into your equation, and then you divide 2.5 by 40 to get into this, and then from here you can change it to log. And from the logarithmic form, you put everything into log 10, and right here, and then you can just simply cross multiply it. And through cross multiplication, then you have t log 05 on one side, and you can divide by log 05 on both sides to isolate t. And when you isolate t, you're left with 2 minutes.
Hey, I'm Allison Mitro. Today we are going to be measuring the pH of lime juice, and we're using these little pH strips that are used for the hot tub, and this hot tub to only go from pH of 6.2 to 8.4, so this is what the color strip reads. So we're going to pour a little lime juice on here. Watch how the pH strip changes. Now if you want to come closer, you can take a look at this. The pH of lime juice is so much lower, more acidic, than a hot tub would ever be. You can see how light it is compared to the pH of the hot tub. That means that this is really acidic. It means it has a really high concentration of hydronium ions in it.
Okay, so because it was too acidic to tell on the pH strip, we looked up the hydronium concentration of lime juice, and it was 3.0 times 10 to the negative 5. Plugging this into the equation, pH equals negative log H plus, we get negative log 3.0 times 10 to the negative 5. Now all you have to do is simply put this into your calculator and get 4.52. Wow, that's acidic. And remember, you have to have 2 decimal places for pHs.
We hope you enjoyed our presentation, and we hope it's very useful in studying for your exam.
Good luck!
Don't fail!